All right. Hi, everybody. Thank you so much for coming to my talk. My name is Jackson, and today we'll be talking about materials in UEFN and how we can use them to work around the limitations of the engine to make elegant and optimized effects that run on all different types of devices. So I also want to say, don't worry about taking pictures. I'm going to have a QR code at the end of the presentation that has all the slides on it, because we have a lot of material code. So starting off, who am I? My name is Jackson. I work with various UEFN studios to develop and deliver polished and optimized maps in Fortnite Creative. I'm primarily a generalist, but I tend to author lots of different shaders to be sure that everything in the map looks nice and animated. So today, I'm here to spend some time showing how I build scalable, performance-friendly material animations in UEFN. So going into what to expect from the session. This is a beginner-level talk, so we're going to start by talking about the limitations of UEFN and then what you have to do to work around those. And then we're going to get into the basics of materials, so like how to make them, how to view the graph, things like that. I'll then walk through step-by-step how to make different material animations in UEFN. After that, I'll talk about how you can make camera-reactive materials that are aware of the player. And then finally, I'll wrap with a few more ways you can go deeper into this type of material animation. So the three main limitations to keep in mind for UEFN are that you're given limited storage size for any custom assets or animations that you have. You're given strict memory limitations for the amount of things that can be loaded in at once. And your project also must run well on all different types of devices, from mobile to PS5. With all this in mind, let's go into some of the different ways that you can animate objects in UEFN. So the first way is with the sequencer device. This is like a timeline-based system. It's traditionally used to make things like cutscenes. Next, you could move objects through verse code, so something like move to or teleport to. You can also animate using the animated mesh device, which plays skeletal mesh animations using an FBX asset. And then finally, you can animate with materials by manipulating the vertices using world position offset output. So kicking things off with the basics, what is a material? A material is it's put on a 3D surface to tell the GPU exactly how it should look under different parameter conditions. So it works kind of like a program that the engine uses at draw time to turn your mesh into a visible surface in the world. So these calculations primarily run on the GPU, which is specialized for graphics and can process thousands of threads at once. So even if you have a huge crowd of different meshes, as long as they share the same material, it'll run pretty well, because the GPU can process all these vertices in parallel using the same shader. So diving into materials, let's go into how to make a material and how to navigate within the material graph. So going over the graph first, it's a node-based canvas that all feeds into the main node. It has all the available shader inputs that you can change to control how your material is going to behave. Materials can be used for all different types of visual effects, but for this talk, we're only focused on the world position offset input, which is used to manipulate the vertices of the mesh. So what is world position offset and how does it work? It's the material output that lets you move the vertices of a mesh in world space, but only visually. It runs on the GPU and happens after all other vertex transformations. This means it doesn't affect the mesh's actual collision or physics. It just tells the GPU where to shift the vertices when rendering. It's super efficient because it's purely visual, so the mesh stays in the same place for gameplay, but you can make it wobble, animate, or deform in any direction with a 3D vector. So to show you what I spoke about from the previous slide, the rendering offset does not actually impact the collision. So you see here, I'm standing on nothing because the collision box on the bottom is in the same spot the whole time. So before we get too deep into material animation, it's important to understand the difference between a skeletal mesh and a static mesh, since it has a pretty big performance impact. So skeletal meshes have skeleton bones and skinning, which allows for bone-based deformation, so each vertex is influenced by one or more bones. All this movement is calculated on the CPU, and this gives you a lot of interactivity, but because it's on the CPU, it's heavier on performance and memory. Static meshes have no skeleton, so they're just fixed geometry, and any animation is done purely visually on the GPU. But the upside is that they're super lightweight because they benefit from GPU instancing. So it can render a ton of them in a single draw call, which makes it ideal for performance-heavy scenes like crowds or environments. Another benefit of using static meshes is that they can be used with Niagara systems. So for example, you could put them on a VFX power-up device to make like a backpack or a hat or something like that. And so when we talk about animating static meshes and materials, we're primarily focused on like the performance-friendly GPU-based techniques and not traditional animation. So a few reasons why this matters for UEFN. Verse and sequences both run off the server, which can have latency issues along with limited scalability since it could possibly bottleneck the server. The animated mesh device uses skeletal meshes, so if you have too many of them, it can lead to local performance issues if you have a lower end device. But material animation runs on the client and it gives you better performance at scale, along with using less project size and memory than a skeletal mesh. So going over some traditional use cases that you'll see in different games. You'll see these shaders used for things like wind-affected foliage, so like trees, grass, flags. You'll see them for liquid surface deformation, so like water, waves, things like that. But then you'll also see them for large crowds where they want to take advantage of the instancing. And then finally for like basic squashing and stretching of an object. So let's get into the editor and start making these materials. So starting off, to make the material, you right-click in the content browser, you select material, and then type the name of your material. And then after that, you can drag and drop it onto whatever mesh you'd like, and then you can apply it to that mesh. So to start editing your material graph, just double-click on the material in the content browser, and it'll put you in the graph, as we see here in a second. Like that. You can then drag and drop your material expression nodes into each of these shader inputs to modify them. So to make an expression, you right-click on an empty space in the canvas, and then you can type in the material you want, and then you can connect them to other nodes or connect them to the main node. So first, we're going to go into some of the expression nodes that we're going to be using in the examples I'm going to show. So first, we have these basic math expression nodes. So you can use these to add, subtract, multiply, or divide values, and then it gives you the output on the other side, which you can connect to other expressions. These two are trigonometry expressions that we're going to be using later. So sine returns the sine of the input. So it will give you like a looping or oscillating movement if the number keeps going up. And arctangent 2 will give you the angle between two different vectors. This is the time expression node, so it outputs the current elapsed time. It continuously increases, so it's always going up. It can be used to do stuff like scrolling textures, but I like to use it a lot, or the cosine node also to oscillate values over time. And then finally, the 3D vector expression nodes are used to work with three-dimensional values. So you can define a static 3D vector with the constant float3 expression. The breakout float3 expression node can split a three-dimensional vector into 3 individual output values for each axis. And the make float3 expression takes in 3 float values and converts them into 1 3-dimensional vector. Here we have a material that's moving this coin up and down. So first we start with a time expression, and then we divide its value by 3. And we do that so that when it goes into the sine expression, the speed is slowed down a little bit for the oscillation. So it looks a little more gradual. And then we multiply the sine value by 30 to sort of amplify the distance that it's traveling up and down. And since we only want it going up and down, we cast it into a float3, but only into the z value. So some more nodes, we have these clamping expression nodes. So these are used for restricting values. So the clamp node will keep the input between the minimum and maximum values, and then the minimum and maximum nodes are similar, but they return the smallest or largest value. We implement the clamp expression here after getting the sine output. So this keeps it inside of that value. So for this, we use the coin's offset and make sure that it doesn't go into any negative z values. So it sort of looks at the coins like jumping off the ground and then sticking to it for a second because it's never going properly into a negative value. Now we're going to go into some expressions that have to do with 3D positions. So we have the absolute world position expression. This gives you the world position of the current vertex. If you only want the position of the actor or the object, you can use the actor or object position expressions. Then you can use the object pivot point to get the pivot point for the object. And finally, you can use the bounding box expression to figure out where a vertex is in an object's bounding box. So if it's at the top or the bottom or the front or the back. Then we have the rotate about axis expression node, which you can use to rotate a vertex about an axis. You need to input the axis you're rotating on, which is a 3D vector, the angle you're rotating it by, which is a float, the pivot point you want to go off of, which is a 3D vector, and then the vertex's position, which is also a 3D vector. So here we have the coin. It's rotating now. So we start with the time expression, which we then again divide by 3 to slow down the speed a little bit. And we feed that into the rotation angle, so it's constantly spinning. And then we're using a constant vector to find that it's rotating on the x-axis, which is up top, and then I change it in the next one to rotate on the z-axis, and now it's rotating vertically. So you're able to modify which way it's rotating using the rotation axis. Now we're using the difference of the object's vertex position and the object's position itself to make it grow and shrink. We multiply that factor by the time expression, which we get the sine of, and then muddle it down a bit to scale it back and forth between 1.75 and 2.25. So it has the scaling effect. So we've gone through basic transformation, rotation, scaling, things like that. Now we're going to go into how you can make interactive materials that can take the camera's data and react to players. So the thing cool about materials is that because they run locally, they can use data to look different to each player. The main example of this is that materials have access to each player's camera position and angle. So you can do a lot with this. You can have them face the player, fade when you get far away from them. You can have them distort when you get close to them. But repeating what I said earlier, keep in mind that it does not affect the collision of the mesh. So if you want them to move out of the way, the actual collision would not move. So you need to keep that in mind. These expressions both give you data about the camera that's currently rendering. So here you're given the world space position of the camera and the directional vector of the camera. These expressions can be used for vector math. So you can use the distance expression to get the distance between two vectors. And then you can use the normalized expression to get a vector with the distance normalized to 1. Here we have this frog that jumps away when it gets too close to the camera. So I'm going to go into how I made this. We start out taking the camera position and the object position, and we get the distance between both these values. And then with that distance, we subtract 500 from the distance and then clamp the minimum value to 0. That way, when you get too far away and it goes into a negative value, it still sticks to the ground. After that, like we did with the coin when it was floating up down, we cast it to a float 3, and we only put it in the z value because we only want the frog to jump vertically, and we have the effect. So now we have another frog. This one will rotate to face the camera as you're spinning around it. So this is all running in the material. It doesn't use any verse. The way that it works is, and I'm going to zoom in. First, we subtract the camera position from the object position and then normalize that. So that sets the vector's magnitude to 1. After that, we get the x and y values from that vector, and we get the arctangent to calculate the angle between those two values and then subtract 1 from it. I'll give you a second for picture. And then after that, we round out these values. So this is how it's only turning every 90 degrees, is we're sort of smoothing it here. Again, because it's not saving any data from previous frames, you can sort of catch it in the middle if you get at a close enough angle. But for the average player walking around, it will turn to face them at all times. You'll see I'll slow down for a second right there. So after that, we put these nodes into the rotate about axis node like we did with the coin, and we put it on the z-axis since it's only turning left and right, and then we use the vertex offset to rotate them. So that's how we do that. And then the second effect that I have are these hands that are mounted to the camera. This is running off of a skin mesh renderer so that I could animate the hands doing actions in game. But hypothetically, you could do it with a static mesh if you'd like, and we'll talk about that in a couple slides with VATs. So as you can see, when I apply the material to the mesh, it locks itself to the front of the camera. So going into how I do that, first we need to figure out the difference between the camera's position and the object's position. And then with that, we move the mesh a little bit forward from the center and down a bit just to fit where I wanted the hands to go, since it shouldn't be inside of the camera. So now we have the pivot point. And then with that, to find the angle, we get the camera's direction vector. We use the arctangent to get the proper direction, the angle that it's facing, and then we add those values to properly offset the rotation so that it looks right. After that, we put all these nodes into the rotate about axis node. We spin them on the z-axis, and then we use our calculated offset for the pivot point and the position, and we have this effect. So now going into more of the optimization end, I wanted to go over vertex colors. So vertex colors are RGB data that is stored in each vertex of a mesh. You can paint directly onto the models these vertex colors, and you can do it in something like Blender or Maya or Unreal's Mesh Paint, and then the shader itself is able to read that. So in terms of materials, you're able to actually mask out vertex colors. So you could, for example, define a certain section that you want to have act a certain way compared to another one, and use the if node here to turn whatever scripts that you have running on or off for that part. So mixing it all together, we have this blob creature that's using the vertex colors, and it has a ton of different moving parts, all inside one mesh and one material. So the eyes are acting differently than like the body itself. There's like little things floating around inside of it. And then as you can see, when you go far enough away from it, it takes in the camera distance and it will like sink into its hat. And it's all, because it's all running on the one mesh and one material, it saves a ton of draw calls. So here's another example. We have this snowman that's like rotating left and right. This sort of builds off the last one because of the fact that it is layering the different vertex colors instead. So you'll see that like the bottom snowball is affecting where the middle snowball is, which is then affecting where the top snowball is. So we can have the vertex colors like take in the individual sections and decide where it's going to rotate and pivot and things like that. And then we combine both of those to have this Cavern beehive object, which it combines what we have from the other two. So as you can see, it does like this jumping thing where it's stretching up and down. While it's doing that, it's also blinking and it's taking in the world position with that. And it's also doing a little bit of global scaling when it lands. So these are all in one mesh and one material. Another really useful thing that you can work with when making materials is to use textures to control your animation effects. So here we have this fish model with a gradient texture, and the point of the texture is to control the amplitude of how far we turn each vertex, each frame. So the brighter areas of the fish allow for more rotation per vertex, and then we multiply it by the sine of time to have the tail of the fish like spin back and forth. So in action, it looks like this. As you can see, the front of the fish isn't really turning, but the back of the fish is taking in the higher RGB values and then using the shader to turn a lot further with a rotate about axis node. So I also want to quickly go over the scalability node for optimization. So you have access in materials to the scalability node, which lets you change materials based off of the power of your device. So if you want to add in extra visual effects to a higher end device versus keeping it simpler for something like a phone or a switch, you're able to do that. And it lets you manage it in one material while still delivering smooth performance on weaker devices and full fidelity visuals on powerful hardware. Now we're getting a bit more complex. If you have an animated skeletal mesh that you want to convert into material animation on a static mesh, you can use a vertex animated texture. So here's an example of a Mixamo mesh that's then animated with a vertex animated texture. So as you can see, it's moving as if it were a skeletal mesh, calculating bone weights, but it's all just running off of a single material. So the way that this works is you generate the texture using the original skinned animated mesh, and then it calculates the offsets for each vertex, each frame, and bakes it into a texture, which the material then reads from. It also will convert your skeletal mesh into a static one, and then you just drag on the material and it works. For Unreal, something to keep in mind is you want to turn off texture filtering for these, because if it makes it fuzzy, it will mess up the animation a bit. So if you ever want to do it, just turn off texture filtering. So to generate them, you can use the anim to texture plugin in UE5 and then migrate it over to UEFN. You could also generate them in Houdini and transfer them over. The way that I personally do it is I generate them with Blender's OpenVAT extension, which has a pre-made material that's compatible with UEFN. So I just bake the animation and it'll give me the static mesh and the material, and I can just drag and drop everything. So this is showing just the scalability, how we have this really huge crowd of individually animated people, and it's running fine. It's really great compared to using a bunch of skin mesh renders, which would like have to calculate bone weights and things like that per frame. One thing to keep in mind, though, is that if you're not careful, these textures can take up a ton of project space. So the two biggest factors are the poly count and animation length. So when you're making the textures, try to look for shorter animations with lower poly models if you're trying to save on storage and memory. Another great thing to quickly go over about using static meshes is that you get Niagara support. So this is an example of me using that beehive mesh from earlier to make a custom backpack for the player using the VFX power-up device. So I was just able to check a few boxes in the material and then drag and drop it into Niagara, and it works like a charm. So you can use it for mounting things to players, or you can make something like a cool animated custom weapon by mounting it to an animated gun on the player's hand. Next, I'm going to quickly go over how to connect this all into level sequences so that you can mix and match different forms of animation. So you're able to define static float nodes in the material graph and then make them publicly editable parameters by right-clicking the node and then selecting Convert to Parameter. This is just how you do it for a float. And then so for the material, I've changed the way that the hat works from the previous version of this blob creature. So now it works with a parameter instead of taking in the camera distance. So you can see that as I change the value from 1 to 100, it gets squished down by the hat until it's just a hat that's bouncing up and down. I'll let it go up to 100. So to connect it to the sequencer, first you just drag and drop it in like this. After that, you click here, you add in the static mesh component. And then after that, you add in the material slot. And then finally, you go in and you add in the parameter, and then you can edit it in the material. So here I am changing these parameters in the sequencer. And as you can see, I'm testing out the animation, and it's working properly just by adjusting the parameters. So it's properly connected. So if I wanted to put it in a sequence, that's how you would do it. So the bottom line of this is, in conclusion, Vertex shaders are very cost effective. They can give some unique capabilities that aren't currently possible in the engine in any other way. And you can make traditional basic animations in the material graph or generate a Vertex animated texture to replicate traditional skeletal mesh animation. There's still a ton of untapped potential in them, and if you know the limitations, you can work around them and create some really visually stunning effects. So that's what I got for my presentation. I've also got a QR code here if you want to see all the slides and take screenshots of the material code. And yeah, I'm happy to take any questions that people have.